about something a little bit different this afternoon. Than you may not have heard about this in a software testing talk before, but I'm a massive space nerd, so I'm just really excited to talk to you about space for the next 30 minutes. Hands up if you think space is cool, just so I get a read of the room. Okay, great. It's very cold, that's true. Good, so I'm among friends here, but I promise is also relevant for the software testers here today as well. But before I get into testing, I want to set a bit of context about the space environment, specifically around satellite technologies. Sorry, this laptop is struggling. There we are. Okay, satellite technologies. So humanity launched our first artificial satellite into space in 1957 with the launch of Sputnik 1. For scale, Sputnik was about the size of a beach ball, about 22 centimeters across, and it weighed 84 kilograms. It was a very simple piece of machinery that just sent beeps down to Earth so that we could track where it was. And this was seen as a marvel of innovation at the time. Fast forward to 2021, we have the launch of the James Webb Space Telescope, which is the largest telescope or largest satellite in space. This thing is huge. It is 21.2 meters long and weighs 6,500 kilograms. So we've come a really long way from the launches of Sputnik. And on top of that, as you can see in the GIF, it's got this really complex unfolding mechanism for its telescope, the gold bit, and its sun shield at the bottom. So space technology has advanced a lot in less than 70 years. And this has led to new satellite-based services. So from a quick show of hands, did anybody use a location service to get here today, like Google Maps or Apple Maps? Awesome, keep your hands up. If you didn't use that, did you check the weather on your phone today? Put your hand up if you did. Okay, fantastic. So whether you knew it or not, you've actually used a satellite-based service today already, and they're becoming more and more embedded in our everyday lives. But I'm sure this probably wasn't a surprise to you. Things like weather forecasting and location services and the use of satellite phones are very well known amongst all of us to be a satellite-based service. They've been around for quite a long time now, 10 to 20 years. But some services you might not know about are just coming into the market. So the newest one is satellite-based internet. So you may have heard of SpaceX's Starlink constellation, which is aiming to provide global internet, particularly in places where traditional internet infrastructure, such as fiber optic cables, doesn't work, so mainly in rural areas. We also get satellite-based TV broadcasting, which is really important for live international events where you want that signal quickly and reliably. So things like the World Cup or the Olympics that we saw last year would rely on satellite-based relays. Some even more innovative services that have come out in the last 10 years. One is disaster monitoring. So this GIF in the bottom right is of the Los Angeles wildfires that happened at the start of the year. And these images were taken from a Sentinel satellite, which is an Earth observation satellite run by the European Space Agency. And we use these images to track the spread of the fire, and we use the data to try and predict where the fire was going to spread so that we could help people get to safe zones for evacuation. And one application that I've only just recently learned about, because it's been going on in my research lab at Strathclyde, is that we use satellite data to help track where ships are in the ocean. This might seem weird. Why do you need satellite data to track where ships are? Well, legally, all ships above a certain size must broadcast a beacon signal to say where they are. And that data can be received by radio frequency link up to satellites, so we know where they are. We then compare those signals with satellite images, and we can say, there's a ship there that's not broadcasting a signal. And that means pirates. So we get space pirates, but not in the way that you expected. And this is a real service that we use, and it protects assets that are out at sea, things like wind turbines that we want to protect from being destroyed. And these number of services are growing. This is just a handful. There are so many more satellite services existing. Things that traditionally were purely on Earth are now relying on space. And this is leading to us having to launch many more satellites into space. So this graph comes from the European Space Agency's annual Space Environment Report. This is their latest one. And as you can see, in the last 7 or 8 years, we've seen a massive exponential increase in the number of objects entering low Earth orbit, which is this region up to 1,800 kilometers. So we start back in the 1960s, and all the way up to sort of the 2000s is when you've got things like the Cold War, the space race between the US and Russia. And the vast majority of satellites in that time are defense or civil. They're being launched for purposes of observation, for war, for defense, and they're being launched by organizations like NASA that are run by governments. In the last 10 years, the vast majority of things we're launching are commercial. So they're providing those services that I've just mentioned before. and the demand is showing no signs of slowing down. It is only growing. And what's great about this as well is that it means we're seeing satellites being launched from non-government institutions. So we've got companies like SpaceX and Blue Origin that are launching these satellites and developing a whole new market for satellite communications and satellite data. And that market's estimated to be worth about 100 billion US dollars and is growing. So it's a really big space. But this is causing some consequences in terms of the satellite population is getting a bit too big. Everyone thinks space is this infinite area that we can use. And yes, the universe is expanding. Low Earth orbit is not expanding. It is a particular band of space around the Earth, and it is a finite space. So as we keep launching these objects into space, we see pictures like this, where you may have looked up in the night sky and seen the trails of some satellites passing overhead. This is obviously quite an extreme example with a long exposure, but it gets the point across that space is incredibly busy. But before I geek out too much about space, what has any of this got to do with testing? And as Andy said, I'm a PhD researcher in satellite communications at the Applied Space Technology Laboratory at the University of Strathclyde. But for 5 years before that, I was a software tester. I worked for Capgemini in Rosen. I was a software test lead. I worked on things like the Iridium satellite constellation. So this is where my two worlds collide. And what this has got to do with testing is I would challenge you to pick a more extreme environment to test for than the cold radiation hell that is outer space. So what has all this stuff that I've just mentioned, the increased use of space, got to do with testing? And that is probably summarized by this slogan: failure is not an option. If you've not heard this phrase before, it's often associated with NASA flight director Gene Kranz and the Apollo 13 mission, which was historically a successful failure, we'll call it, where a lot of things went wrong getting the astronauts back from the moon, but they managed to salvage it together. It made a really good film, if you've not seen it. It's not proven that Gene Kranz ever said this, but it's kind of more widely associated with the space motto of space is an extreme environment. You can only launch things once, so you need to get it right before you launch. And this is the overall test philosophy for any mission critical area, not just space, but a lot of this stuff comes from space. You only get one shot and we need to make it right. So how do we actually do that with testing? It's not just a philosophy, how do we implement it? And to start thinking about how we implement it, we need to think, well, why do we test? What are we testing for to make sure that failure doesn't happen? And in a mission critical setting, we're mainly thinking about safety and resilience. So this GIF on the side shows every object orbiting the Earth that is larger than 10 centimeters in size. And as the animation goes on, more objects will come in that are above 1 centimeter and smaller. So as you can see, it's a growing population. It's very busy. So we need to make sure that anything we're launching into space is safe in this environment, safe from the debris, safe from the temperature changes, from the radiation. And we need to make sure it's safe because all of those services I mentioned at the beginning are dependent on satellites. Could you imagine what happened if all of our GPS satellites suddenly went down? The world would come to a standstill. Not many people know how to read maps nowadays. We wouldn't be able to get to the places that we're going. People couldn't get to work. And because of that, we also need to make sure our systems are resilient so that if one satellite does get knocked out by a piece of debris, we're not losing global access to these services. But on top of the physical things that we test for, we also need to test for regulatory compliance, which is the boring side of it, but something that we have to test for in a mission critical environment. For things to be able to go into space, they have to be qualified as flight ready. Regulation is really important. And once it's in space, there's all sorts of regulations about what orbital levels you can go for, how long your mission lifetime has to be, what you have to do with that satellite or with that spacecraft once it comes to the end of its life. But as you might see from this diagram, it's a bit of a mess. While space technology has come a long way in 70 years and we've got these really cool unfolding satellites, space governance has barely changed since the start of the space age. To give you an example of that, if you had 2 satellites owned by different people coming into a near miss situation in orbit, well, what currently happens, and I'm not joking, is that that signal will get transmitted to a ground station where there will be an operator who then emails the people that own those satellites and ask them via email to make a decision on what needs to happen. So it's very manual, it's very political. There's no necessary black and white here. It's a very gray area. And as the space population continues to grow, that's not something we can rely on. It also makes space systems really difficult to test because there are lots of these gray areas. There are some legally binding treaties, some non-legally binding guidelines, and it's really complicated to know which ones you need to test for. So it's really important that we do our best to get it right. So how do we test for these things? Well, this might seem a bit counterintuitive, but we need to be agile. In a mission critical setting, you might often think of things like waterfall models and linear development, and you do your development and then your testing. But actually, with the way that space is evolving, and we've got all these new types of constellations being launched, all these new regulations coming out, we need to make sure that we can test in a way that is agile and flexible to those changes so that we're not slowing the progress of innovation. And on top of all of this, we've got to do it in space. Space is a very different environment to testing here on Earth, and one that is notoriously difficult to replicate. It's very difficult and expensive to make near 0 Kelvin environments, near vacuums, etc. And it's very expensive to launch. So we need to make sure we can make our tests as accurate as possible. So how do we actually go about doing this? What does testing a space system look like? Well, I've mentioned before that we need to be agile, and this is generally the slogan that underpins the aerospace industry. Test as we fly, fly as we test. And what that means is we do our development and tests alongside each other. So they're not separate tasks, they are inbuilt from day one. And again, this might go against what you think of mission critical, where it's slow and testing takes a long time. But if you think about it, and we know this to be true, that bugs are more expensive to fix the later we find. That is 1,000,000 times more true for space, where these missions cost millions, if not billions of pounds to produce, decades of time, decades of manpower, and also national pride can be at stake for large missions if they go wrong. So it's really important that we're testing as early as possible. But this is more difficult in space systems because they're all so tightly coupled. All these components do not ever operate in isolation. If you've got, say, a telescope mounted on a satellite, you need to make sure that telescope is away from the solar arrays, so you've got power. You need to make sure everything fits inside a spaceship for launch. You need to make sure that all the components can cope with the vibrations of launch. And so we need to make sure we're doing integration and system testing as early as possible. So it's very much a shift left mentality that some of you might be familiar with, but it is applied to space, and it has been since the very beginning. And on top of all this, we need to do this in a representative environment. So test as we fly, fly as we test is about making sure that we make things as accurate to space as possible. And there's two main ways that we do this. And the first one is a use of models. Here we go. I'm hoping this will play. Here we go. This is my model of the International Space Station from my Lego set that I've built. And so we understand that models are not exact copies of the real thing. They may be smaller, cheaper, simpler, maybe only focusing on 1 or 2 key properties of an overall system. So my Lego space station, I accept that that is nothing like the International Space Station, other than maybe in appearance and scale, but it's not orbiting the Earth, the solar panels don't work, etc. But we rely heavily on models, granted more complicated than this, because they are just easier to produce, it's less risk, but it still gives us that overall system view that we need to be able to test something confidently. And whilst we may not use Lego, we do use similar models. So this is NASA's Neutral Buoyancy Laboratory in Houston, Texas, and it contains a life-size replica of the International Space Station. So a bigger version of my Lego model, but it's in a neutral buoyancy pool that's 12 meters deep, and that is so that astronauts can get in the water and experience a similar effect to microgravity. So they're floating around, they can practice their spacewalks on the edge of the International Space Station and practice their tasks that they're expected to do, whether that's installing or repairing a component. And what's interesting about this is when we think of astronauts, so this is Rosemary Coogan, who's a Northern Irish astronaut in reserve at the moment with the European Space Agency, who's training to go to space. She's also a tester. She's not just an astronaut. If we think about it, she is testing that her spacesuit is working, that it's not letting in any water, which would be the vacuum of space, and that she's able to operate in it. She's testing the component she's going to install on the International Space Station, which, whilst not 100% accurate, is as close as we can get. She's also testing the procedures. So have they got correct instructions? Are they in the correct order? Because everything in space is all about procedure and checklists. So is that working? So astronauts may just be some of the coolest testers that there are. But not all the models we use are like this. They're not all physical. Some can be virtual software-based models. Some can be a hybrid. And they come in varying levels of complexity. All these models are complex, so I've said less complex to more. I don't think there's anything simple about space. But these are all the types that we technically use when developing a space system. So I'll just talk you through a couple of them. The simplest ones at the top are mock-ups. So these might be used to construct a basic design of a spaceship or a satellite, identifying which components need to go where, getting the configuration right. We also have virtual mock-ups of things. So we like to use virtual reality, particularly for crewed missions. So making sure that the crew have got correct access to get into a module like the Soyuz to be able to get in and out of it correctly, or for moving around things like the International Space Station. We'll use virtual mock-ups for those. And then as we move down to more complex, we get into structural and thermal models. So this is where I mentioned that a model may focus on one key property of a system. The structure and the thermal properties are the singular most important things for a space mission. Everyone thinks it's radiation. It's the number one thing that people think of when they go to space, but actually, how are you going to get there in the first place? If your system can't cope with the vibration of launch, it's not structurally sound, you don't need to worry about radiation because it's never going to leave the atmosphere. Likewise, if it can't withstand the thermal heat, if it can't withstand the heat at launch of the flames that come up from the bottom of the rocket, if it can't cope with the thermal shift as you move from daytime into nighttime without the protection of the atmosphere, radiation is going to be the least of your problems. So we like to develop models early on that focus on those. And then in the bottom half, we get more into integration level models. The suitcase model is my favorite purely because it actually does go in a suitcase. It's a model that is kind of the first iteration that accounts for function and form, but it generally fits in a compact way so that this system can be sent off for integration testing at the launch site. So if you're developing a satellite, for example, you put the key components together in a suitcase, maybe a larger suitcase than that, send it off to the launch site, and then they check that it can fit within the spacecraft that's going to take it. They check it can be deployed correctly. Or if you were building a system like for the rocket itself, you would send it to the launch site to make sure it fits with the tower and that all the other interfaces are going correctly. We then move down into the electrical and functional model, which may be of interest to software testers, because this is where the software comes in. The software doesn't come in till quite late usually, because we need to make sure we've got the hardware right before we can even think about putting code onto it. But this model is making sure that if we're collecting any data, that the transmission is correct, it's not being corrupted, and that any code that's used to automate things, such as the unfolding of the James Webb Space Telescope, that that's all functioning correctly. And then at the very bottom, from the engineering model downwards, these are all known as qualification models. So these are your full system in form, fit, and function. These are the ones that you use to verify that your whole design is actually working, that it's launch ready. So these are incredibly complex, incredibly expensive. Things like your ISS model in the buoyancy pool, that would be down at this level, where you've already had to sort of get past all these initial hurdles to get here. But we don't always use all of these models. We use different combinations of them for different development and testing approaches. So the most complete approach is the prototype approach, which uses all but one model. The prototype model is gone. This is very expensive. It's very complex. It's very thorough. So we would only usually use this model in a case where you've got a brand new or complex technology, something that's been completely untested before, where you're not sure what's going to happen, or it's a really low risk. You want really low risk. So something that maybe is a case of national pride, or maybe there's people on board and you can't afford any level of risk. You would go for a prototype approach. But however, most people don't go for this approach just because of how expensive it is. We tend to use a proto-flight approach, which only uses 3 models, which it reduces cost. You haven't got to develop all of these other things, and it reduces time, but it increases risk, because essentially your proto-flight model is the one that gets flown. So this one may end up in space at some point. And that means your qualification and engineering qualification models go through your destructive testing. So they'll get shaken for acoustic testing, they'll get blasted with radiation. So you haven't got any backups. With the prototype approach, you've got loads of models that you can test. And so if something goes wrong with your flight model, your qualification model might be able to go to space instead. But with the proto-flight approach, if something goes wrong with your proto-flight model, nothing can go to space. But this model is being used a lot more, particularly in the new space era, which is that era where we've got all this commercialization. Because when you've got satellite constellations like Starlink, where you've got thousands of satellites that are the same, this model works really well, because if you just destroy one in testing, you've still got thousands of them. So the risk gets mitigated through production. Sorry, the slide would move. Okay, yeah, got it. Cool. So as I mentioned before, qualification is really important. Nothing can go through to space without being qualified at this system level. And because of that, that means things do get slowed down. So a fact that I wanted to bring up here is that even as late as the 2000s, software in the space sector lagged about 20 years behind software in the tech sector because of how long it takes to qualify a part. So you develop a part, develop the software, and it takes so long to get it qualified that technology has moved on 20 years before it actually gets into space. That lag is reducing now, but is still part of it. So to help reduce that lag and help things catch up, we like to reuse pre-qualified components. And the testers in the room will have probably already identified that there is a pitfall that comes with reusing technology. Okay, that is not playing, but it's okay because the pictures tell you the story of what's going on anyway. So this is the Ariane 5 rocket, which was launched on the 4th of June, 1996. And as you can see, it did not go very well. And the reason that the rocket self-destructed 37 seconds into launch is because some software engineers decided to reuse some code from the previous rocket, the Ariane 4. The Ariane 5 was a lot faster than the Ariane 4, and it did so the reuse of the code did not account for the extra speed, led to an integer overflow, which then caused a self-destruct mechanism to be implemented because the error was handled incorrectly. This mistake cost the European Space Agency $370 million and is known as one of the most expensive bugs in the history of software. So whilst reusing components can save time, can make test effort easy, we need to make sure that we're still being thorough and that we're making use of regression testing. But this is something that's only relatively new to the space sector because we don't actually have that much test data to learn from. Space missions are so bespoke and still relatively quite rare. So we're still learning from previous mistakes and uncovering new things all the time. And another recent example, will this one play? Let's find out, folks. No, it won't, but that's okay. This is the James Webb Space Telescope, and it went through an acoustic test, like I mentioned. It was shaken to make sure it could cope with the forces of launch. And during its acoustic test, 10 washer nuts came loose. And you might think, not a big deal. You can buy 10 washer nuts for a few quid and everything's going to be fine. No, this led to an 800-day delay on the project at a cost of $1 million a day. So $800 million for 10 washer nuts. And that's because these systems are so tightly coupled that the washer nuts coming off was actually just a symptom of a much larger problem in the wider system that then took nearly 3 years to re-engineer and fix. But because we've never built anything like the James Webb Space Telescope before, we couldn't have foreseen this coming. But what we can do is use this information from these tests to make future missions better. And one way we do that is through open test data. So this is just one database. This is NASA's Lesson Learned database, which records everything that's gone wrong for NASA in their 70-odd year history. So they record where it's gone wrong, what happened with the components, so that other agencies, not just NASA, can learn from their mistakes and we can make space safer and make testing easier for the future. I mean, if you were doing your jobs and you didn't have previous test data, I think everyone's jobs would be a lot more difficult. So by making this data open and giving people larger data sets to work from, we can improve testing, make things more resilient for the future. And also, as I mentioned, the population of space is growing. And as we continue to launch more things and do more testing, this test data set is also only going to grow exponentially. And with that, the final thing I want to talk about is what else is going to change in the new space era. So everything I've talked about so far, using models and history and test data to learn and test space systems, works really well for traditional space systems of 1 or 2 spacecraft going up together. But it's not fit for purpose for the new space era that we live in with this commercialization. But what else are we going to be needing to test for? Well, if you thought you were going to come to a space talk and not hear about Katy Perry, you were wrong. So space tourism is a really rapidly growing industry. It's set to bring in millions or billions of dollars to the space industry in the future. And it's something we need to test for. If we're going to be sending not just people, but people with 2 days of training to space, that's a whole other wealth of things that we need to be testing for to make sure those people are kept safe. Because nobody's going to want to go to space on holiday if there's a really high risk of death. So we need to be making sure that we're developing tests that can account for these things in the future. We've also got the rise of mega constellations such as Starlink, which are thousands and thousands of satellites. Starlink currently has about 7,000 in orbit. They want 40,000. So it's a really big change. And with that, satellites are becoming less bespoke. They're becoming more standardized. One standardized model of satellite development is a CubeSat, which is shown here. They're about this big. They don't weigh very much, but can do really complex things. And they all come with standardized hardware. So that combined with the number means that rather than testing each system in a bespoke way, developing 10 models for each one, we can actually just do quality control on our manufacturing processes. We can do sample testing. We can do regression testing, finally, on space systems to check for common errors, rather than needing to go through this really complex process every time, which reduces the cost of testing and the risk. And lastly, the privatization of the space sector is the biggest change. We couldn't do many test flights in the past. Government agencies like NASA don't like to spend taxpayer money blowing up spaceships. Elon Musk loves to do it. SpaceX has a lot of money, so they can afford to do lots of test flights. They can afford for their spacecraft to blow up and their company is still going to survive. And they can learn from those mistakes faster and iterate quickly. So rather than having failure as not an option, they have fail fast, learn fast. Let's get things into orbit quickly. Let's iterate as quickly as we can and learn from our mistakes. So if anything, maybe failure is an option in the space sector after all. We have much more money, more experience, and we're learning. Failures are not the catastrophic setbacks in the space sector that they once were. And we're living in a time of innovation from private investment, and we have nearly 70 years of experience in spaceflight. So in my opinion, failure has to be an option if we're to keep testing enough to cope with the rapid deployment of spacecraft into orbit.